Right, Matrix, we are moving on. We've looked at the shapes of the graphs and we've also looked at the relation of equations to predict changes. And now we are moving on to look at techniques for graph analysis. How do I get information from a graph that they give to me? Now, there's three techniques that you can use to get information from a graph. And the first is to read from the graph. If they're asking one of the variables on the graph, then you just read from the graph. If they ask, you take, for instance, this momentum velocity graph. If they ask me, what is the momentum when the velocity is a certain value? Then you say, okay, so the velocity, when the velocity is 20, and go and read what is the momentum. So you can read from the graph. That's the very first way to get information from the graph. Right, second way to get information from the graph is to use the gradient. And especially if it's just through the origin, we'll talk about graphs that's not going through the origin. But at the moment, if we've just got graphs with the origin, to get the gradient, you will also say delta y divided by the delta x-axis. So it's the change in the y-axis divided by the change in the x-axis to give you the gradient. And when you look at a graph, how do you know what is represented by this? Now, take, for instance, this momentum versus velocity for an object, right? There, m was your constant and p was directly proportional to v, and the graph looked like that. Now, what does this gradient represent? Now, gradient is always whatever is on your y-axis, which is p, divided by whatever is on your x-axis, which is v. And we use the equation p equals m times v. So p divided by v is just m. So p divided by v is just mass. So here the gradient represents the mass. Right. If they had this the other way around, then it would have been 1 over m, but we'll see examples of that. Next, you can use the area underneath the graph. Now, with gradient, we had the y divided by the x-axis. Here, you have to multiply the variables of the axes. Right, so here, say for instance, you've got current over an ohmic resistor versus the potential difference, right? Now, we know R equals V over I. So if it's a ohmic resistor, that means that R is constant, then they are directly proportional, and that's why we got a line through the origin, right? But now they are not asking us what is the gradient of this one. They're asking what is the area. So I'm not going to work with that anymore. I'm looking for one where you have I times V. And if you know your equations, or if you've got the information sheet, you will know I times V is P, power. So here, the area underneath the graph represents the power. So if you, for that resistor, you've got the current, you can read the voltage over the resistor, but you can also, from that triangle, work out the power. Now, you've been using this for a long time. This is not something new. For example, when you had movement graphs, right? For movement graphs, you had the gradient, right? If you're on an xt graph, the gradient was x divided by t, and that was the velocity, right? So to do that quickly, we said x, v, and a. You go from an xt graph to a vt graph by using the gradient, right? And the opposite, when you use the area underneath the graph, then it gives you the change in velocity, right? So you had to start out and say, I am on whatever graph, and then what do I need, right? So you're on a VT graph and you need A, it will be the gradient of that graph. If you're on a VT graph and you need X, change in X, that will be the area underneath the graph. So that you've done already in grade 10. Okay, moving on. Let's just do 3 quick examples where we are going to use that, right? First one there, was in the November 2016 paper. The learners investigate the relationship between current and potential difference at a constant temperature for three different resistors, X, Y, and Z. The resistance are Rx, Ry, and Rz respectively, and they obtain the graph shown below. And now comes the question. Which one of these conclusions regarding the resistance of the resistors is correct? Now, if we look at that, that's an I times V, right? I versus V. So what does this gradient represent? Here, the gradient will be a change in I divided by a change in V. Now, if I look at Ohm's law, R equals V over I. Can you see it's the other way around? So the gradient over here is 1 over R. So the bigger the gradient, the smaller the resistance. So that one has got the biggest gradient, and that will mean the smallest resistance, right? So X has got the smallest resistance. Okay, so immediately you will say the answer is A. Z has got the smallest gradient, therefore the biggest resistance, and they asking us for from big to small. They're definitely not the same because they don't have the same gradient, right? So the answer was A. Moving on. Plastic containers with different masses are pulled over surface A, and the graph shows the kinetic friction on the containers with the normal force. Okay, stop the bus. What do we have? They are pulling things with a force. And what do we have? We have a friction in the opposite direction on the surface, sorry. Right, you've got the kinetic friction. And now, what does the kinetic friction depend on? Well, for kinetic friction, you have the equation mu k times n, right? And when you're on a specific surface, that mu is a constant. It depends on how smooth is my surface, right? Smoother is a smaller mu, right? So what is the relationship between F and N? They're directly proportional. So you get a straight line through the origin, but the bigger the mu, right? The bigger the gradient, because how do you work out the gradient over here? Over here, the gradient would have been a change in fk divided by normal, and fk divided by normal, that will be mu k, right? So now they repeat this for a surface B, and they ask, is surface A smoother or not? Now, what do we say? A has got a bigger gradient, right? Which means that A has got the bigger uh, coefficient of friction, right? And if it's got a bigger coefficient, it means A is rougher, right? More rough. So is A smoother or not? Not. And referring to the graph, so you will say it's got a bigger gradient, therefore it's got a bigger coefficient of friction, and therefore it's a rougher surface. Right, moving on. A constant current is sent through an ohmic resistor. Ohmic just means the R is constant, right? It's not determined by the current flowing through it, right? So through it. Draw a graph of the charge, Q, moving through the resistor versus time, right? So you've got your T there. So you've got Q charge is measured in coulomb and time in seconds, right? That the current flow through the resistor. So R is a constant. Right. So you're looking at Q and T, and you've got an equation that says Q equals I delta T and a constant current. So my current is constant, and therefore my charge is directly proportional to the time. And I've got a straight line through the origin. And now they ask, what does the gradient of this graph represent? And the gradient will be something Q divided by something T. And what is Q divided by T? That is current, right? So the current is represented by the gradient of that graph. I hope everyone is happy. That is just how I use it. So remember, you can use the gradient and you can use the area and you can read from the graph. For gradient, it's y-axis divided by x-axis. And for area, you are going to multiply the axes. Right, moving on. Now, how about a straight line that is not going through the origin? Now we are moving on to straight lines, but straight lines with y-intercepts. Now, the graphs we've drawn up to now had no C. They only had a straight line through the origin. They were just directly proportional, which told me if x doubled, then y doubled. If x decreased with a factor 3, then y decreased with a factor 3. They increased and decreased with the same factor. But now that I have a C extra, a C that is not 0, then they can not be directly proportional to each other because it's doubled and something extra is added. So if you double the x, it will not mean y doubles as well. Right, so the moment that you get C not 0, you will end up with a y-intercept. And how do we draw graphs and what do we know about the gradient and the graph with that one? Now, the first example we're going to look at is with photoelectric effect. With the photoelectric effect, you've got a piece of metal. You shine a light on that metal and we're only looking at one photon, one particle of light falling onto that metal, giving all its energy to one electron on the surface. And then if that energy is more than the work function that is required to release that electron will be released. If you give it more than what is required to go, it might even have something left over to move around with, some kinetic energy. And now you're asked to draw a graph of kinetic energy for that for the photoelectron that is released from a specific metal. Well, specific metal, that's just one with a specific work function. Every metal's got a different work function. So if they say specific metal, it means that work function is a constant. Right, and we must draw that versus the frequency of the light source. So you're drawing the kinetic energy of the released electron versus the frequency of the light source. Now that's going to give you a straight line, and I want to write an equation in the form of the straight line y equals mx plus c, so that I know what is represented by the gradient of the line and what is represented by the y-intercept of that line. So I'm starting out with the equation they give us on the information sheet. On the left-hand side, that E, that is for your photon that you put in, right? And on the right-hand side, what does that electron do with the energy? It will use some to climb out, right, to be released, and then the rest will be used for moving around. So this is what the electron does. Now I've got that. And I'm asked to draw a graph of kinetic energy versus frequency. So I need, in the y position, I need kinetic energy. And in the x position, I need frequency. So I need to rewrite my equation to get to that shape because I need to have a straight line formula there. So kinetic energy over here in front and frequency there. Now let's see. It's the frequency of the light, and light is on the left-hand side. So I'm going to replace that with HF to get that F that I need in my equation. And then I'm going to rewrite it, taking the work function over to the other side, makes it minus, and switch the two sides around. And I end up with the kinetic energy equals to HF minus the work function. That immediately tells me the gradient of this line is now going to be h, Planck's constant. Right. Now there's no graph over here because if you've got a frequency lower than threshold frequency, no electrons are released. So there's no graph. But if you were to extrapolate back to C, you will see that this would have had a y-intercept at minus the work function. So this is how you use that equation to get to the equation that you need. The next one is an example is typically the one that we use for determining the EMF and the internal resistance of a cell. So what we do is we set up this circuit and we've got a rheostat over there, a changeable, a variable resistor. And the reason why we use that is to change the current. That is the work of the resistor, of the rheostat, to change the current. So immediately when you do see the rheostat over there, you know that current is your independent variable. It's the one that you are changing. And now you are asked to draw a sketch graph to show how the potential difference over that cell, that voltmeter reading, varies with the current through the circuit. So you've got the voltmeter reading over there and you've got the ammeter reading over there. Now, when we want to draw this line, we need to know how to write it to get to y equals mx plus c. What do I need on the y-intercept is a voltage. We'll talk about that potential difference now. And in the position of F, I need a current. Right, now let's just talk about that potential difference. What is that potential difference? What is measured by that voltmeter? Because you are drawing on your graph what you measured from that voltmeter. Now, if the switch is open, then you are measuring the EMF, right? Because if no current is flowing, then it means no energy is used in the cell, and that voltmeter will read the whole EMF. But the moment that you close that switch, the movement of the current through the cell will require some energy, right? So there will be lost potential difference, lost volts, right? What we also call internal voltage, right? And what that one will measure is actually only what is left over for the outside circuit. So it's actually measuring the external circuit's voltage. What potential difference is used in the external circuit, right? It is the EMF minus what is used up inside that is available for outside. So when we have to write it in this way, we need to have V external in front, because that is what we draw on our graph, and then something I plus something. Okay, let's see. What equation do I have? I know that the EMF is the voltage that is used internally and the potential difference that is used externally, right? EMF is everything that is given by the cell. Some of that is used inside, V internal, right? We also sometimes call that the lost voltage. And some of that is used externally, sometimes called the load. Now, if you look at this one, I want the VE there, right? And I want I. Now, how can I get an I in there? EMF is just a constant. So this will be I times R plus VE. You are replacing this with Ohm's law, right? Using Ohm's law to replace V with I times R. And that R is obviously the internal resistance. And now I just have to rewrite to get the VE in front. So VE will be equal to, take this over to the other side, it becomes negative, and then I'm going to write the R before the I. Why am I doing that? Because I want the I in that position of X. So then I end up with having the gradient over there and the Y-intercept over there. So if you go and draw this graph, it will be a straight line, but not a line through the origin. So you will have a Y-intercept there, and your Y-intercept is just your EMF, which makes sense because if you've got a current of 0, then that voltmeter will measure the EMF, right? And the gradient over there is minus R, which explains why we have a graph like this. If the constant was positive, it would have been going up, right? But the constant is negative. You've got a negative gradient there. Right, that is the second application. Right, now we are going to do a last example, and that is on Newton's second law of motion. So we're all talking about F net equals m times a. Now they're telling you that an applied force is exerted on the box. Let's put an A there, definitely applied force in a horizontal direction, and the box experiences a kinetic frictional force, right there on the surface, right. The magnitude of the applied force is changed, right. So that is my independent. I am putting on different forces over here, exerting different forces, and the acceleration is measured. So that is my dependent. And then what are they giving? What are they keeping constant? They are working with a box, right? So mass is constant, and they are staying on the same horizontal surface. So, well, mu k and therefore fk is also constant because your surface is the same. So that is also constant, right? Now, draw a sketch graph of acceleration versus net force. Remember this y-axis versus x-axis. So I've got acceleration on that one and F net on that one. F net in Newton and acceleration in meters per second square. So even though you don't do a detailed graph, it's just a sketch graph, just the shape, don't leave out the units. It's very important to still put the units in there. Right. Now, what does the gradient of the line represent? Okay, so we know it's a line, but let's start and look at this. Acceleration, net force. The equation that I have that's got both of them is F net equals M times A. Yes, and we're working with a box that's telling me M is constant. And immediately I will say F net is directly proportional to A. Right, so that tells me directly proportional straight line, and it is going through the origin. Then what does the gradient of this line represent? Now we're looking at the gradient over there. The gradient over there will be y-axis divided by x-axis. Now, how can I get from this equation A over F net, right? A divided by F net means I have to take M over to the other side, and that is 1 over M, right? So this is the inverse of mass. Moving on, draw a sketch graph of the net force versus acceleration. So now I've got F net over here in newtons, and I've got acceleration in meters per second square over there. Right, the equation F net equals M times A. M is my constant because I'm working with the same box all the time, and F net is directly proportional to A, straight line through the origin. Right, but now this time, what does the gradient of this graph represent? So here the gradient is change in y-axis, which is F net, divided by change in x-axis, which is A. And over there, you will see F net divided by A is equal to M. So this time the gradient is equal to the mass. Right, let's make this more interesting. Now I'm not asking the net force, I'm asking the applied force. So now we have F applied in Newton and acceleration in meters per second square. Right, I know my equation, F net equals M times A, but now I don't want the net force, I want A. So remember, we are working towards Y equals mx plus C. What do I need in the Y position? F applied. What do I need in the X position? Acceleration, and then there can be other things, right? But that needs to be. So first, let's look at F net. If I look at this one, obviously there's a gravity down and a normal force up, but I'm not going to bother about them because they are going to cancel out. They make zero, right? So if I add all the forces together, I'm adding only actually the forces in the direction of movement. And I've got my applied force that is in the positive direction, and then I've got friction that is a negative force because it's working in the negative direction. So for F net, I'm going to add my forces together. That is Fa in the positive direction and minus Fk, the friction, and that is equal to M times A. But I'm working towards Fa on its own. Okay, so Fa, and that will be Ma, and I'll take the friction over, and it becomes Fk. All right, so immediately there I've got the gradient and there I've got the y-intercept. So I'll have a positive gradient and I'll have a y-intercept that is actually the frictional force. Now, does that make sense? Yes, it makes sense, because remember, if you are pulling, right, and you are pulling exactly the same amount as the kinetic friction, it means there will be an F net of 0. And if F net is 0, it means your acceleration will be 0. So if the applied force is equal to the magnitude of the kinetic friction, then we are just with F net 0 and A is going to be a 0. Right. Okay. Now, the very last one, the very interesting one. This time they want acceleration versus applied force. So let's look at this one. I'm looking at acceleration in meters per second square versus applied force in newtons. And once again, I start out with F net equals m times A. We're still working with the same box. So Fa is my positive and friction is my negative force. So this will be F applied plus minus friction equals to m times A, right? And what am I working towards? Let me just keep in mind, I'm working towards mx plus c, but now in the y position in my equation, I need an a, right? And in the x position, I need f applied. Okay, so let's rewrite this to get into that one. So I need a on its own, right? It means I have to divide the other side by m. So this will be Fa over m, and that will be Fk over m, right? Okay, but I have to rewrite with a in front, so let's write with a in front. A equals, right, take it over to the other side. What do I need there? Fa on its own, something in front, so this will become 1 over m times Fa, and then minus Fk over m. So immediately there, you've got your gradient is 1 over m, and you will have a y-intercept. And that y-intercept is negative Fk divided. Right, so you will have a positive gradient, and remember, we don't have the negative part of the graph, but if you extrapolate it, right, dotted lines, so it will be like this, okay, with your friction over there. Right, so the gradient of this line is 1 over m, right? And the y-intercept is minus Fk divided by m. So they are really now asking us strange graphs. They're giving you strange things in the exam. 1 over current versus the total resistance or things like that. But don't be baffled. Just go and say, what do I need in the x position? What do I need in the y position? Write down the equation from the information sheet and rewrite and even substitute if necessary until you get into the y equals mx plus c form, and then you will have the answer. So I hope you will have fun with graphs.